This terminal recording illustrates the reality of the vibe coding trap. You ask an AI agent for a simple feature like input validation, and instead of a minor edit, you get this chaotic cascade of code. You step away for 2 minutes only to find the agent refactored your entire data layer, introduced 3 new abstract classes, and completely polluted your Git history. This outcome isn't the result of a hallucination or a misunderstanding of the codebase. The agent is simply operating within the vacuum of the original prompt. When there are no structural rules governing its behavior, the AI defaults to maximum autonomy. It iterates and refactors because nothing told it to stay within a specific scope. Researcher Andrej Karpathy points out that AI coding agents do not operate poorly by nature. Rather, their default state is unconstrained execution. When an LLM generates massive technical debt, it is rarely a lack of capability. The core issue is autonomy without accountability. Software engineer Forrest Chang distilled Karpathy's observations into a practical open-source solution. The fix requires injecting a static, declarative behavioral constraint file into your workspace. You execute this straightforward fix by dropping a file named CLAUDE.md, or .cursor rules, directly into the root of your repository. Mechanically, the AI agent is forced to read this document at the start of every session. You dictate exactly how it behaves before it processes a single request. This file acts as a standing set of rules, enforcing 4 specific architectural principles: explicit reasoning, strict simplicity, scope isolation, and goal looping. Deploying this constraint file alters the execution graph of an LLM session. You stop dealing with an unpredictable text generator and start working with an accountable engineering partner. The first rule is to force explicit reasoning before any code gets written. An LLM's most dangerous behavior is silently picking an interpretation of an ambiguous prompt. It will confidently execute a guess, and by the time you review the output, you are already negotiating a rollback. This diagram maps the voice agent problem. Without constraints, an AI silently selects a heavy stack, lighting a path through LangGraph, DeepGram, and 11 laps. That skips critical decisions. Did you need Twilio or WebRTC, a native SDK, or a multi-turn workflow? We see the same failure in data modeling. Tell an AI to store a user's location, and it defaults to 7 decimal places. That precision identifies specific doorways, introducing immediate privacy liabilities and unnecessary database bloat. The behavioral constraint is strict: state assumptions out loud, present multiple interpretations, and halt execution to ask. Forcing the AI to surface these choices requires about 90 seconds of developer decision-making. That brief pause saves hours of complex system rework later. The second rule is simplicity first. AI models often demonstrate their capabilities through over-engineering. Left unconstrained, they inject speculative features, single-use abstractions, and error handling for scenarios that are logically impossible in your specific architecture. An AI will eagerly implement a heavy tool like LangGraph for a lightweight single-turn API execution, when a simple native SDK is the correct choice to minimize latency. In an unconstrained geospatial workflow, the AI pulls raw geographic data into Python, passing massive GeoJSON payloads to the LLM. The correct architecture uses PostGIS to execute spatial joins internally, passing only a thin, lightweight result to the LLM. To enforce this, the constraint file must dictate ruthless efficiency, write the absolute minimum code, include 0 speculative features, and if a 200-line output could be achieved in 50 lines, force the AI to rewrite it. This constraint forces the LLM to act strictly as the orchestrator, rather than the compute engine. It eliminates the vast majority of AI-generated codebase bloat. The third rule is surgical changes. We are targeting the high-risk behavior of drive-by refactoring. You ask an agent to fix a single regex expression, it fixes the regex, but while it's in the file, it reformats adjacent functions and renames variables you never asked it to touch. To stop this, we apply the mental framework of a Google Kubernetes engine migration. A disciplined infrastructure engineer handles a migration by cordoning the old nodes, draining the pods, verifying the new pool, and deleting the old nodes in isolation. We map this to the codebase. The AI executes one targeted action. Adjacent, poorly formatted functions remain strictly untouched. There is one critical operational nuance here. The AI must clean up unused imports caused by its own modifications, but it must never delete pre-existing dead code unless explicitly instructed. Enforcing this surgical isolation ensures your Git diff remains clean and reviewable. It prevents your codebase from drifting away from your team's established standards. And the fourth rule is goal-driven execution. Large language models struggle to follow step-by-step human instructions over long contexts. They drift and make unauthorized substitutions, but they are exceptionally good at looping toward a verifiable target. Executing a large task without verification checkpoints is dangerous. We see this in database administration with massive Postgres imports. Kicking off a massive Postgres import inside a single transaction block runs until memory exhausts, triggering a total rollback. The out-of-memory killer terminates the process. 12 hours of compute produces 0 committed rows. When you define success criteria up front, like instructing the system to confirm batches of rows are committed before proceeding, you surface failures in minutes rather than hours. Take a production telephony agent. You set a loopable constraint. The end-to-end latency must remain under 800 milliseconds. The AI will iterate architectures until it hits that specific, measurable threshold. This changes the interaction from imperative instructions to a declarative goal. You no longer give the AI a list of steps, you give it a verifiable state to achieve. Fix the bug becomes write a failing test, then make it pass. Vague goals produce unusable results. Measurable success criteria produce resilient, deployable systems. There is a core engineering trade-off to this approach. Implementing these 4 rules explicitly slows the AI down. That friction is entirely intentional. You should bypass these rules for trivial tasks. The overhead isn't worth it for a typo fix or a single-line configuration update. But for any multi-step logic on existing shared codebases, these guardrails are the only way to prevent silent, compounding structural damage. Karpathy's core insight holds true. The AI does not lack capability. The constraint file doesn't limit what the model can compute. It establishes necessary accountability. This simple file defines exactly when the agent acts, how much of your system it is permitted to touch, and how you will verify its completion. By defining exactly when the agent acts and how its work is verified, the CLAUDE.md file moves the AI from an unpredictable generator to an accountable tool. It creates the baseline of predictability required for any shared production codebase.